Hello everyone, thanks for attending my talk. My name is Andrea Mambretti and today I'm going to present you our work on transient execution vulnerability checkers. Before going into the details of my talk, I would like to thank my co-authors, Pasquale, Alessandro, Alexandra and Anil from IBM Research and my advisor, Engin Kirda from Northeastern University. A special thanks goes to Pasquale because this work was heavily based on his master thesis. So I would like to give you an example of what a transient execution attack is. And to do so, I'm going to use a Spectre BTB. Spectre BTB, as all the other transient execution attacks, is a microarchitectural attack, which means that takes place in the backend of the CPU. And in particular, Spectre BTB targets the branch target buffer, which is a microarchitectural component within the backend of the CPU that is used by the CPU to speculate the possible target on indirect calls and indirect jumps whenever the real target is actually not readily available, which is basically means that it's not cached. So if we assume that the victim encounters one of those instructions, what is going to happen is that instead of waiting for the real target to be loaded from memory, the process that is running victim, the CPU that's running victim is going to query the branch target buffer and is going to get a possible target. And the CPU will start to speculatively execute at that location meanwhile waiting for the data to come from memory. And then when the real target will come, they will just compare the two locations, and if the guess was correct, then everything that was executed will be committed, otherwise everything will be rolled back. Now, the catch behind the Spectre BTB is that if we introduce an attacker in the picture, an attacker can influence the value inside the branch target buffer. Through some training on the CPU, an attacker can force, during a Spectre BTB attack, some value inside the branch target buffer. And then if later on the same CPU, a victim again executes one of those instructions that have no readily available possible target, it might query the value from the branch target buffer that the attacker actually inserted, which means that victim is going to start speculatively execute at the evil location. This allows an attacker to basically redirect the speculative execution of the victim wherever he wants. And if this possible location contains some side channel code, then the attacker might be able to leak some information out of the victim. This type of attacks can be performed in different scenarios, and this table represents some of those cases. For instance, the very common is users versus kernel, where a user process tries to attack the kernel, or another common one is users versus users. So the idea is that the user process is trying to leak some information out of another user's process, and so on. So as you can see, there are many ways this attack can take place, and this is true for all transient execution attacks. Luckily for us, we have several mitigations available now for transient execution attacks. We have software mitigations, hardware mitigations, and just think that for Spectre BTB, we have more than 6 applicable mitigations. So why so many mitigations, right? The reason behind this high number of mitigations just for a single attack is that these attacks can be performed in different settings, and there is no mitigation available that works for all the possible scenarios altogether. The idea here is that if we want to try to verify if a system is actually vulnerable against transient execution attacks, the situation is very complicated because we will need to consider all possible scenarios in which these attacks can be performed and make sure that each one of them has the right mitigations in place. To alleviate the burden of such a heavy task, the community developed tools that allows us to automatically verify, automatically check the security of a system. There are two main categories. The first category is called empirical, and it comprises of all those tools that uses proof of concept implementation of the attacks to verify if the attack is present on the machine. There are two kinds of empirical tools, one that uses a cache cover channel, and the implementation, the current available implementation is a tool called Transient fail. And then we have on the other side a tool that uses a performance counters to verify if the proof of concept implementation attack worked or not. And in this case, the tool is called Speculator. However, these empirical tools have some limitation, because what they really do is not telling us if the system is exploitable or not, if there is an exploitable vulnerability or not on the system, but they are telling us only if the attack vector is present, but they don't go and verify all the other conditions that are required to perform transient execution attacks. This is because they run their proof of concept implementation in just a synthetic scenario. So we are not able to take that result and then map it to one of the use cases we saw before. On the other side of the spectrum, we have instead the information gathering tools. As the name suggests, these tools collect information from various sources, the CPU and the kernel. And for instance, from the CPU, using the CPU ID instruction, they try to verify the microcode version, and based on that, understand if the system is updated or not. And through the kernel, with the procfs interface, they try to verify which mitigations are available on the system and which one are enabled. And in this category, the tools that are available under this category are called the Spectre Meltdown Checker and MDS tool client. Let's have a brief look to the Spectre Meltdown Checker output for Spectre BTB, the attack we briefly discussed before. And as you can see here, the tool was able to verify that IBRS and IBPB, two hardware mitigations, are actually enabled and active and used by the kernel, as well as the kernel that is running on the system is compiled with red Pauline. Given all this information, the tool is telling us that the system is actually not vulnerable to Spectre BTB. However, here the results is actually not very accurate, because in our previous work published at WOOT 2019, we were able to demonstrate that despite what Spectre Meltdown Checker is telling us, this Spectre BTB attack is actually still possible. And here the reason is that this tool, Spectre Meltdown Checker, as well as MDS tool client, they focus only on one use case of the one that I previously described. They only focus on the users against kernel. In our work, we show that we can still mount Spectre BTB despite what the tool says in a user versus users scenario. This shows how, if we rely solely on the output of a Spectre Meltdown Checker, we might get misled from the tool to think that the whole system is actually secure against the Spectre BTB, but in truth, only the kernel is actually secure against it. So we provide in our paper a complete analysis of these tools, and here are the pitfalls we actually identified. First of all, the use case imprecision. So none of the tool consider all the use cases I presented at the beginning, and they only focus on the users versus users to kernel use case. As I was saying before, for the empirical tools, the empirical only focus on the attack vector, and they don't really tell us anything about the actual vulnerability status of the system. We found that the gathering tools suffer from parsing errors. This is because the kernel interface keeps evolving and is heavily developed. And therefore, for instance, we found that the MDS tool client was misparsing some information, and due to the format change that happened in the interface that MDS tool client was using, the tool was telling us that the system was actually secure while it wasn't, and this is because there was like a desynchronization between the source and the way the information were parsed. This tool also suffer from cache noise, and this is a specific problem of a transient fail that uses a cache cover channel to retrieve the success of its POCs. So whenever the system, whenever we are running a transient fail, we will need to make sure that in the system there is a lot of cache activity, because otherwise that might destroy the signal that that transient fail is trying to read from the cache. Speculator instead has the limitation that relies on the program counter interface, and this interface is not available everywhere. For instance, in a virtualized environment, it's generally not available, and so we cannot use a speculator and its methodology there. And finally, some of these tools, Speculator and Spectre and Meltdown Checker, to correctly function, they require root privileges, which means that only the administrator of the system can actually use them. Basically, none of the available tools, it's complete to tell us the full picture against transient execution attacks. And so we decided to provide our own tool that we call GhostBuster. That is, its goal is to basically prevent all the pitfalls we identified. GhostBuster is not a new tool, but is a hybrid tool that put together the two methodologies. And as you can see, it leverages a Spectrum Meltdown Checker from the gathering tools, and Speculator from the Empirical tools. For Speculator, we wrote not only the performance counters tests, but we also wrote the cache-based test, so that whenever we cannot use the performance counter interface, we can actually use the cache cover channel to verify. And whenever we can use both, we use them both to correlate the results. And GhostBuster has a final stage where we aggregate all these results and we map them through to the use cases we identified that were not considered in previous work. Here is an example of the output of a GhostBuster for a Spectre BTB. And to be noticed here is that we provide information about which settings we are running the attack. For instance, here is a cross address space. The attack could be run also in a same address space, and so on. We provide information about the success rate of the synthetic test, and we also provide the isolated success rate for instance, some of the requirements like the spatial collocation and temporal collocation. We also provide the difficulty level, which is based on a new metric that we introduced that consider all the possible requirements that the attack has, as well as if there are implementation of these attacks in the wild. And based on this, we can say how hard it is to pull off a specific attack. And then finally, we provide our suggestion and our results per use cases. Whenever we cannot say anything, we provide a suggestion on how to manually verify the security of a system for a use case. Otherwise, we can say that the system is vulnerable or not. To conclude, we provide the first analysis of transient execution vulnerability checkers. We provide a recommendation on how to correctly test a system given that none of the previous methodology was bulletproof. We provide a meta tool, a new meta tool called GhostBuster that enhance the existing tools. And finally, in the paper, we also provide a large-scale analysis of the top 16 commercial cloud providers, and we verify the security of their default instances. And with this, I would like to thank you for the attention, and if you have any question.